I've talked about it a little bit with this class, but just to make sure that we're kind of all on the same page. We do have this one kind of final unit. It is the intro calculus unit. I've done various different things at different points, but we have enough people who are going on to calculus, particularly a couple of people who are going on to AP, where they will kind of need to be exposed to this in order to not be pretty drastically behind. And if you're going into not AP Calc, then you'll be a little bit ahead. You're going into the dual enrollment, which will be nice and comfortable. Yeah. That being said, I did not love the idea of having you guys take like an extra like full test and quiz that the seniors wouldn't be taking, particularly on something that can get to be a little bit tricky, as we'll kind of see towards the end of this unit. And so what that means is that I'm not taking more grades, I'll say, other than the classwork grade and the homework grade, than what we would have seen with the seniors. So it's the same number of quizzes, same number of tests. You guys are taking an extra quiz and an extra test, which means you get an extra quiz and an extra test dropped at the end of the quarter. So for seniors, they got 1 quiz and 0 tests dropped. You guys get 2 quizzes and 1 test dropped for this. So this is if this goes really, really poorly, then it cannot hurt you. If it goes really, really well, then it can help you quite drastically, which is good.
Wait, the test from this quarter?
Yes, from this quarter.
All my quiz, I have 1 bad quiz and all my other quizzes are good.
Okay, well then you get a mulligan if the calculus quiz goes particularly.
Yeah.
Okay. Now we are going to be starting today with something that is going to feel like kind of redundant and trivially easy, and like, why on earth would we be talking about it? Hopefully I can very quickly demonstrate that this is going to be something that is in fact novel and also worthwhile. And it is very much the cornerstone of every single thing that you do in calculus. Kind of under the surface, under the hood, behind every single like operation is the idea of limits, which we are going to kind of establish today. Now, we have already talked about these, not necessarily in these terms, but we have talked about things like limits. And in fact, the day 4 material that we're going to be doing is going to be taking the content that we've already seen with limits and putting them in this language. So just kind of like emphasizing some of the stuff that we've already talked about. But for now, we're just going to work on kind of getting a general understanding. This is one of those things that's kind of tricky to define in a way that is particularly useful. And so what I'm going to do, I'm going to give you guys the notation, and then I'm going to show you guys an example, and hopefully you can kind of connect the two, and it's going to be a little bit vibe space, but that's okay. We're going to start with the idea of a one-sided limit, which can come in kind of 2 different flavors. There is the left-handed limit, and then there is the right-handed limit. So a limit from the left, as well as a limit from the right. The way we denote a left-handed limit is as follows. We say lim, and then we denote that our x value is approaching some other value. Normally that's a number. And to say that it is from the left, we do a little minus sign, almost in like the exponent here. It's a little minus right there. Limit as x approaches a, in this case from the left, of a particular function f of x. Which we can translate to be saying that this is the limit as x approaches a from the left. The left-handed limit we denote with this little minus. means we approach from the left. Any guesses then for what the right-handed limit would be, how I would denote that? Same thing, but with a plus, yeah. So the limit as x approaches a, with a little plus here, of f of x is literally the exact same thing. It is the limit, blah, 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 blah. But now, blah, 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 from the right. So just copy and paste all of that. Okay. So let's take a look at an example. And I think this example is a really good one to start with because it highlights, one, the difference between the limits and like what we've been working with, and kind of gives us a little bit of insight into why this language might be useful for us kind of moving forward. So let's take a look at example 1 here. We are given an absolute mess of a function. This would very much be piecewise. It's probably piecewise in like, well, I don't know, like 4 or 5 different parts for different regions of its domain. Very, very crazy function going on here. And we're going to hone in on what is happening, kind of the general idea, what is going on at -3. And let's start with a question that we can probably answer just straight away, although maybe is a little bit tricky in this context. Be a little bit careful. Let's try to fill out D first here. What is f of -3? Or why does this question kind of not really make sense in this context? So what is our function when x is -3? And is this a problematic question for me to be asking? What do you think, Harrison?
Is that a whole?
It is a whole at -3. And so if we are trying to figure out what our function is doing at -3, we can't answer that question. In fact, our function is undefined at -3. Right? There's nothing there. Little open circle, nothing to talk about. And you have that sometimes with functions, right? Sometimes you have these values that are missing, sometimes you have gaps in your function. But that doesn't necessarily mean that we can't say anything about what we would have been expecting to happen at negative. In fact, if you're looking at this whole, you could say something about what your function should have been doing, or something that your function you would expect it to be doing if in fact we were defined at -3. And this is where the limit becomes incredibly, incredibly useful. The limit doesn't care about what's actually going on at -3. Right? Our function could be not defined at this point. It could be defined in a super weird way, like maybe it's following this path, and then just randomly like jumps up. I don't know. It'd be a weird thing to happen, but it certainly could happen. Our limit ignores all of that. It says, I actually don't care if we know what's going on at -3. I don't care if we can know what's going on at -3. All I'm concerned about is what should be going on at -3. What would we expect to be happening at -3? And so we focus on the values around the x value concern, not the x value itself. Most of the time, that's going to be completely like redundant. But there are some corner cases like the one we're seeing here where we can't directly talk about what's happening here. We can talk, though, about what it should be, what we would expect it to be. So let's start with A here. We are looking at the limit from the left as we approach -3. When I'm talking about a limit from the left, that means I'm starting a little bit to the left, nudge a little bit to the left of -3, and then kind of run from there. So we could think about kind of moving in from the left here. And as I get closer and closer and closer and closer to an x value of -3, what is the y value that I'm getting closer and closer and closer and closer to? I'm getting closer and closer and closer to 4, exactly. So we would say that the limit from the left as we approach -3. Well, I will answer that with a statement of see if you can't pick out where on this graph that might not be the case. Sometimes it will match, but sometimes it won't match. Can you identify a point? Yeah, where maybe it's not going to match. And even five, what's going on at 5 is kind of funky, and we'll maybe look at that later. 5 would also not necessarily match because what's going on to the left of 5, we have no idea, right? But okay, so we have looking a little bit to the left, and we can also look a little bit to the right. And as kind of Andrew has observed here, what's going to be true as we move in from the right-hand side of this point as we move in, it's also going to be 4. In this case, in this particular case, and I would say in most cases, it's going to match. In the vast majority of cases. So there are a couple of examples on this graph, and I would say, take a moment to say, where here would we not maybe see this trend? And most of the points we see this trend, where would we not? Where do we see different behavior to the left or to the right? Okay, questions here with just like our basic idea of the limit, like what it is, how I'm finding it. All that. It's kind of hard to define, but hopefully not hard to understand. Not too crazy. Just yet. Give it a second. Okay, then take a stab at E, F, and H. So skip G for now, but try the exact same process that we just did. Try it at x equals 0 as well. You're saying, what's happening if I nudge a little bit to the left and then follow my line? What's happening if I nudge a little bit to the right and then follow my line? And then where is my function actually defined? Which doesn't matter. E, F. Yep, I agree with those two. So of those, so yeah, skip G, and then of those two, which one is actually used to tell me my output? Yeah, perfect. Perfect. So of these two, I would say we used one of those. But no, sorry. So this is probably correct. I was saying for H. Sorry, great. I believe you know that. If we're slightly to the right of 0, where would we start? Give me a start point and then what y value. So if we're a little bit to the right, maybe starting like over here-ish, and then moving towards the x value of 0, what's the y value that we converge to? It's kind of helpful, like, well, what's the, as we go to the x value of 0, what's this y value that we're approaching? So you trace with your pencil for a little bit to the right? And we're tracing inward towards 0. If I follow the line to the x value of 0. Tracing towards 0, right? We're approaching 0 from the right. So we're just going to inwards along this line towards 0.
Pay attention to that.
What's the y value that we're approaching?
Got this. And then we can put it on the quiz and test, get our worst.
Perfect. Very nice. Very nice. Very nice.
Trying to figure out the other ones, but I'm confused.
Yeah, we haven't defined what an actual limit is, so we'll need to do that. I like that. Yeah. And then H, perfect. Very nice. So this, if I nudge a little bit to the right and then follow the line, what's the y value that I'm moving towards?
American history.
Is it is the y value that I'm moving towards undefined?
It's negative.
I'm moving towards -1. So when I'm like in a neighborhood that's a little bit to the right, I'm moving toward -1. And then whatever happens at -1, I'm kind of finished. Or what happens at 0, I'm kind of blocked. You trace the line, but you don't actually care what's going on at -1. So it'd be negative, exactly. Because we're approaching -1, even if we never actually reach it. Okay. Perfect. Very, very nice. Very. Here, of these two, it doesn't need to be those two, but what would our function actually tell us is going on?
Well, it's gonna be, you said that same thing last weekend. Every weekend, every weekend. Yeah.
Not in terms of difference, like in terms of like just like
Yeah, that's
or that's what they go for this. I think one
Those
thing.
things, be a hooligan.
It's.
Damn right. Every good chat, right?
That's every time.
It could be empty, empty, and then there's another point that's filled, it could be empty, empty.
Getting.
It's just.
I'm getting good doing that.
There's no way you just did this.
Yeah.
All right, very, very nice. Oh, I'm terrible with my left and rights too.
Yeah.
I don't understand people who can just like get them instantly.
Like naming.
No, like miss.
Like naming things left wall, right wall, like, wait.
Well, what I do is I twitch my thumb. This thumb is slightly less reactive than this one. So it's a really quick check for me. This one feels thicker than this one does. Just like it's not as responsive, like it doesn't move quite as well. Because I've like jammed this hand like a lot. Well, probably like tennis. Probably tennis. I know he's the sponsor for tennis. Oh, that's cool. That's super cool. Yeah, I heard the coach is pretty intense.
Yeah.
Which is cool. All right, let's take a look here at E, F, and H. Let's start with the one that we kind of did before we even thought about this idea of limits. If I'm asking what the function is actually doing at 0, what is the output that's going to happen when x is equal to 0? Yeah, it's the one that's like filled in. Thing to note, it doesn't need to be one of the two limits that we're about to define. These could both be open, and maybe my output is like up here, and then it would be what, like 5? Sure, that's like possible, a little bit weird, but that's the point of limits, is to deal with functions that are not behaving particularly nicely. And so in this case, it does match. We'll see one of our limits does not need to actually. It doesn't even care about the limits. Our limits don't even care about what's going on at 0. But in this case, we'll see it. All right. Looking to the left, I start a little bit to the left of my point, and then I move inward. So what do I approach as I start to the left and move inward? I'm approaching +1. And what do I approach? And here's kind of the tricky thing. It's hard to look at this and think of this as like one nice graph. It feels like it's a bunch of separate graphs, but this is one function. And so we look at what is the path that I'm following when I start a little bit to the right and move inward. What is that y value that I approach? It is -1. Nudge a little bit to the left and move inward, nudge a little bit to the right and move inward. You're just looking at, what am I getting close to? And what we've seen is that, okay, sometimes it matches. In fact, often it matches. Most of the time we would expect it to match, although I guess I could come up with a weird function like Dirichlet's function that's doing who even knows what, which is gross and terrible. But most of the time we would expect the limit from the left and the limit from the right to match. We will. But sometimes it doesn't, right? Certainly. Okay, so then there's the question of, we have our one-handed limits. What then am I asking for if I ask for the limit itself? So like, these are the pieces to the puzzle. The actual question that I'm more likely than not to ask you is, what is the actual limit as we approach a particular point? For which, this gets a little bit technical. If you're a little bit confused by the jargon, we can go over it, more than happy to. But this is kind of a definition. It's mostly a definition. It's how we see this. So we would say that the limit as x approaches a of f of x exists, is equal to L This is probably like the most technical way we would define that it exists and is equal to a particular value. One of my favorite things to use in all of math. If, which is, again, this is getting a little bit technical. This translates to if and only if. It's not just me. This is what you will find in like math textbooks if you are getting to this level. If, which is essentially to say that this statement is true if the following statement is true, and it's only going to be true if the following statement is true. So if the following statement is false, this must also be false. And if this statement is true, then this statement must also be false. Essentially, both of these things need to be happening in order for us to be happy. And if one of them is happening, then the other is guaranteed to be happening. They're like tied together, which is why it's a definition. It's like if one is true, then the other must therefore be true and can only be true if the other one is true. And this is if the limit from the left exists and matches the limit from the right. Feels super technical. It's way more clear than, this is why the trickiness with limits, it's so easy to make it feel so much more confusing than it is. This is very straightforward. Looking at the limits that I've given, the left-hand limits and right-hand limits, do we have an instance where my limits agree? Yeah, they agree at -3. The left hand agrees with the right hand. Both of them are saying 4. Therefore, the overall limit is also 4. Whereas, what is going on with E and F? They're different, right? 1 and -1 are not the same. And since I don't have agreement from the left and the right, here we would just say, get your mean girls ready, that the limit does not exist. This is what is done.
Yeah.
Feels a lot less impressive when you actually see the machinery under the hood. Okay, so let's take a look at I here, which is taking a look at what is going on at 2. We are being asked, what is the limit as x approaches 2 for this particular function? What do I need to show to establish what the overall limit is? I need to show them from the limit from both directions. I need to do a one-handed limit from the left. I need to do a one-handed limit from the right, and they need to match for the overall limit to exist. Okay, so what is the limit as x approaches 2 from the left in this case? What is the like y value that I'm getting really close to here? It is 2. What is the limit as x approaches 2 from the right of this particular function? It is also 2. I'm also getting to 2. Moving in from the right, converging to the same point. Therefore, what is my overall limit? Because they agree, because they both exist, my overall limit is 2. What's actually going on when x equals 2? The whole, it's undefined. Does that affect my limit in any way? No. It could be filled in. and my limit would still be 2. It could be somewhere else, and my limit would still be 2. The limit doesn't care about what is actually going on at that value, which is why it's really, really well equipped to handle things where things are working normally, which is cool, but also things where or places where things are breaking. I should say places where our function is misbehaving. So it's nice when it's behaving, cool, but also we're fine if it's not. And that's kind of the power of limits. Yeah.
Do we have a finals class or?
No, we do. Yeah. SDCs are like AP classes now. So the SDC test was like the final, but also has nothing to do with the grade, just like the AP exam. It's nothing to do with the grade. Right, questions with limit basics from a graph? Not too bad.
That wasn't that bad.
Yeah.
I finished when you get first, but.
Hopefully not too much worse today. I mean, maybe Monday we'll get a little bit tricky, but we'll work through it. It'll be good. It'll be fine.
Those that didn't come today, should we tell them to stay?
Yeah, be really, really scared.
They're talking about these still here.
Okay. Let us then continue on to our second example, which is a little bit more like the actual like stuff that we are going to be working with. What we're going to find, particularly kind of moving forward, is this is generally not how we handle limits. There are algebraic ways to deal with limits much more effectively. Specifically, direct substitution is the most common way to deal with limits. And there was someone in second period who, for example A, worked out how to do this with direct substitution when I hadn't even mentioned what direct substitution was, which was super, super cool. But you wouldn't be able to do the same thing for any of these others. The main issue that we are running into is that every single one of these x values that we are trying to talk about is one of those problem values. Right? Sometimes the limit and the function get along very, very well. Sometimes they do not. And it is for these cases that we are looking at here where they are not getting along well that the limit is even worth talking about at all. Because otherwise, why would we even care if they just always get along? All right. So what is the issue? Just kind of first and foremost, just to get us ready a little bit for Monday. What is the issue that we are running into with every single one of the x values that we are kind of approaching here? They all make us, yeah, there are x's in the denominator, and as such, they all make us divide by 0. Every single one of these x's that we're trying to kind of figure out what's going on here, every single one makes us divide by 0. Okay. Okay, so the limit then is especially tasked for handling things like this, but we don't have a graph. And okay, maybe we could do a graph on our calculators, and that would be fine. By the way, if you don't have a calculator, we certainly could kind of construct a graph that would maybe be a little bit imprecise, as we're going to see here. And so we would like a maybe more refined, a slightly better way to approach. Of course.
Oh, yeah, with that.
This is pre-tolerance.
Good stuff. Okay, so any ideas? Yeah, we're just gonna yeah, simultaneously, it'll be good. Any ideas for how we might deal with the fact that we need to figure out what is going on with our function while not having like a clean picture? What could you do to figure out what is going on around the point that we are concerned with? So we could algebraically manipulate it. That is what we're going to do on Monday. There's an even more like brute force, like caveman way to approach this, which is what we're starting here. Even more, we've got our calculators in hand. We're trying to say what's happening as I'm getting really, really close to 9. How could we see what's going on as we're getting close? Say again? Plug in, well, if we plug in 9, we divide by 0. Plug in 8, which gets us relatively close. What could I do that's maybe better than plugging in 8? 8.9, which gets us pretty close. What could we do that's maybe even better than 8.9? 8.99. And so what we're going to do is you are going to plug in values of x that get you closer and closer and closer and closer to the target value that you're looking for. We're almost done with this example, and then I'll be able to like actually focus on this. Sorry. Okay. My advice, personally, and you'll see this pay off for the final example that we're going to look at here. My advice would be 2 values to the left, 2 values to the right. Would be my personal advice. When I got very proficient in this, I just did a value that was super close, but I kind of needed to be able to know and diagnose when that was giving me something that was kind of wrong. And so doing a double check, having 2 values to just kind of double check yourself is good. If you did 3 values, that would maybe even be better. So let's take a look at this. Do this. Okay. So we are trying to figure out what is going on the limit as we approach the square root of x minus 3 over x minus 9. And we are just going to plug in values super close. I liked 8.9. I'm going to do 8.9 and 8.99 to figure out what's going on to the left. And we'll do 9.1 and 9.01 to figure out what's going on to the right. So this is the square root of 8.9 minus 3 divided by 8.9 minus 9. We get 1.671-ish. Exact same thing, but I do 0.99 instead of 0.9. We get a little bit closer, and we get 0.1667, blah, 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 blah. So if at 8.9, this was 1.671, at 8.99, 1.667. What value do we seem to be approaching? And you can, if you're not 100% sure just yet, you could plug in one with even more 9s, get an even better view. But what does it seem like we are getting closer and closer to as we get closer and closer and closer to? 0.167, or maybe even like, and this maybe is a little bit hard to distinguish, maybe 0.16 repeating. But like 167 would also be totally acceptable. I would 100% take that. Yeah. So like you could really see this if you did like a bunch of 9s like this. It's getting really close to 0.16, repeating, which is the same as 1/6. So this would be the limit as x approaches 9 from the left of this particular function, which is 1/6. We are looking for the overall limit, though. So I checked what's going on to the left. What else do I have to check? What's going on to the right as well. So the exact same thing, but if we're a little bit to the right of 9, that's going to be like 9.1, 9.4, 9.1. And this will also be 9.1. And we get 0.1662. And we get a little bit closer, be 1/100th of the way off, 1/100th of the way off, 0.1666. What does it appear that we are converging towards? Exact same thing. And so, because the limit from the left matches the limit from the right, we would say that the limit as x approaches 9 of this particular function is equal to 1/6. Then there would be no limit. And you'll find that there are some examples in here where that is the case. You would need to show left hand and right hand. You need to check values to the left and values. 2 is pretty reasonable. As soon as you're confident that you know what the answer is, then you can stop. You'll see, we'll look at the very last example here. You should not have a whole lot of confidence in your answer. And as you check more and more, you're going to lose the confidence that you did have. So we'll see this. In this case, limit, though, is 1/6. Okay, so questions with finding our limits for the equations just by this brute force, plug in something super, 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 super close to the value that is in question. How does this feel? Kind of annoying that you're having to do this one I definitely characterize as annoying, but not necessarily all that strenuous. We'll do the algebraic stuff on Monday again. That kind of bypass it. All right, take a stab at B through this first E. Sorry, I made a little typo. So these 4 here, exact same process. Pick values that are really, really close. All of these are centered around 0. So something a little bit to the left of 0, something a little bit to the right of 0, and then plugging those in order to check.
I already know.
Absolutely. I've got here. We'll start up. Yeah, we'll start up.
In the Cooper's. So you plug in. I don't take like stuff, 800 or so what do we notice that walking in? When they were 7. What James won the championship.
So you're right, that it is converging. It feels like it's not.
The Patriots rookie Will Campbell has worn the same pair of underwear per game since.
It is. You gave me sure like this.
Yeah, I assume he just wore the same pair.
How does it not have holes?
I don't know. Sophomore year in high school, he's in the NFL. So it's like 6-7 years.
No. And then what does the E want? Like it's close.
Does Will Campbell move since he's scrambled?
No, he's a lineman.
Yeah, so what is this?
Oh, I thought it was quarterback.
Now our name, your back.
And then the answer goes to.
Also one.
Well, they run separate grade.
But again, like the 0.01 was
Separate MCL sprain.
Okay.
Not my goat.
Oh, sorry, take over. This purpose.
Yes,
So for these, would it be like 0.01?
exactly. 0 point, I would do 0.1, 0.01, and then positive, negative to check those. Okay. Yep. Okay, this looks good. So what are we getting
Your bonbons?
as we are?
Hey.
Yeah, that seems to be like where you repeated.
Yeah.
Seems like we're getting closer. So this limit, we check both sides. Okay, so this one definitely agreed.
Oh my
Point
God.
nine repeating is.
Oh my God.
Point nine repeating is also.
Really? No.
Well, I would certainly not. That's, they're literal.
Ah, no good.
And then
I don't
there's no,
care.
you know, left hand, left hand. Seems good, and then just checking the right hand.
Bro, I volunteered at, old people.
Alright,
This was a stop sign or
So what are we?
We had to sing that to them at the end. Bro, they were getting so bad. We had to.
His had like a little, like a tiny
It
bag.
was.
Sure.
She told her.
Yeah.
But on.
What do we eat?
Are we doing?
Point one.
Whichever one you want.
Second, but yeah. Second. I didn't.
Who's it?
Oh,
Bond.
Like, like food. It's just so annoying. Like, I understand it, and it's just that, like,
We'll be able to do a lot of them algebraically. These ones, which is why it's important to go with this. But if we can't do it algebraically, this is how we can. Yeah, but a lot of them we will be able to do
like when
algebraically.
you, like, if, as x approaching 0.
Yeah.
Negative would be approaching from the left.
Yeah.
That's literally like,
I think the little
Yeah.
assigned to program one instead of two.
Okay, so looking at B here. What did you guys do in order to check what was happening as we kind of move in to the left? How'd you do this? Yeah, plug in like negative 0.1, negative 0.01, that seems super good. So make sure that I'm in radians here, which we are. Okay, so this would be sine of negative 0.1 divided by a negative 0.1. I get like 0.998. And then we could do the same thing, but with some zeros. Some zeros right here. We get 0.99999. What appears to be the limit as we approach from the left. Okay, so you could definitely say 0.999 repeating. That is fine. That is equivalent to 1. Yes, so the limit as x approaches 0 from the left of this function, I would classify that as 1 if you said 0.9 repeating. Okay, and then we'll do the exact same thing, but we'll try from the right instead. So I'm going to delete negatives, and we get the exact same thing. Actually, the exact same numbers, which hopefully makes a lot of sense since sine is an odd function and dividing by another odd function. We're getting just the exact same thing, that the limit as x approaches 0 from the right is also 1. And so since the limits both exist and agree, the overall limit would be 1. What did we get for C as I'm plugging in basically the exact same values? Same thing. Yeah, left I'm approaching 1. Now notice here it's a little bit different. This is actually a subtle difference that we'll see is important. That here I'm approaching from below 1 in both cases, right? 0.99999 is getting really close to 1, 0.999 is getting really close to 1. Here, I have one side where I'm approaching below and one side where I'm approaching above, but I'm still converging to 1. I'm still collapsing on 1. Either can happen. I could have approached above and above. That's totally fine. I could do below, below. I could do below, above. That's totally fine. Here, we also find that the limits agree that we are closing in on 1. Okay, this one we don't really need a calculator for. We can kind of do this one by hand. So let's try this. So the limit as x approaches 0 of the absolute value of x over x. Let's do the left-hand limit first. So what would it be a good value that I could plug in to check what's going on here? Sure, like negative 0.01. What's going to happen when I take a negative number, small negative number, take its absolute value, and then divide it by its negative side? So it's going to become -1, right? Turn it positive, divide it by itself, but negative. Positive divided by negative is negative. Number divided by itself is 1. This limit does exist and is -1. What's going to happen on the right-hand side as I'm doing this exact same thing? It's going to be same process, but instead of a positive divided by a negative, it's going to be a negative divided by, sorry, a positive divided by a positive, which is giving me +1. So my limit on the left exists, it's -1. My limit on the right also exists, it's +1. Therefore, what do I say about my overall? The overall limit does not exist. because they don't agree. Okay, and then cosine of x minus 1 over x. I'm assuming we probably didn't quite have time to get to that. That's fine. We can just showcase this really, really quickly. So cosine of 0.00001. I'm going to get a little bit lazy here. -1. Actually, I'm going to make sure I'm getting too lazy. Do the fraction cosine of 0.0001. -1 divided by 0.0001 gives me a very, very small negative value. We could check the other side as well. In fact, you should check the other side as well. And in fact, you should probably check more than 1 point just to make sure, but this will be pretty corroborating that we get basically the exact same thing, but positive and negative. And so what would this limit be here? What does it feel like it's collapsing on? So there one's positive, one's negative, but that's okay. I can approach the same value from above and below. It feels really close to 0, right? And if you weren't sure, if you were looking at that, like, I'm not sure that we're approaching 0. That's why it's important to have more than one reference point, because like, how do we know what we're approaching? Plug in a value with more zeros and you'll see it. Okay, questions with the first 5 here? Kind of tedious, but hopefully not like crazy. What is that? Okay. Not my care. Care is meant for the stress you've been. Okay, let's take a look then at our final example, which I messed up, and this should be example F, but that's fine. Limit as x approaches 0 of sine of 1 over x. What should I do? Let's plug in some values. Let's do 0.1. Let's do 0.01. Let's see what we get. So sine of 1 over 0.1. Okay, I get that. I do sine of 1 over 0.01. I get this. Does it feel like we're maybe converging to a particular value? Maybe we are, right? Maybe it's like 1/2. Maybe it's -1/2. That's possible. Okay, what should I do to check to see what's going on the other side? Same thing, but make it negative. Yeah, sure. Let's do sine of 1 over negative 0.1. Okay, let's do sine of 1 over negative 0.01. Okay, we got the same thing, but the opposite. So now it doesn't really feel like we're converging, I wouldn't say anyway, to -1/2. Maybe we're converging to 0, but we're pretty far away from 0 to be making that kind of claim that we're converging towards 0. What could I do then if I'm kind of not really sure what's going on? What could I do to like get even more sure? We could graph it, certainly we could. We could plug in one with even more zeros. Let's try getting closer. Let's do sine of 1 over 0.001 now. And we get something completely different. We go in the opposite direction of where we came from. Okay. So what on earth is going on here? Well, if we were to graph this function, and we were to zoom in around 0, we would get a mess, a massive mess. That is a little bit indicative of what we saw previously about what was going on around 5. So I mentioned that this limit would be really, really hard to compute, particularly from the left, because of how chaotic the left-hand side is. What's really cool there actually is that that term that I just used, chaotic, is not a casual description. That is a literal description of what is happening. This is a chaotic system to the left-hand side of this value, just like how this is a chaotic system around zero. Another way to say this, you don't need this for this class, but it's cool because it's like on the cutting edge of like a bunch of different disciplines, is that this is a function around zero that is deterministically sensitive, which is to say tiny, tiny, tiny changes in where you start have drastic changes about where you end. You'll notice that the difference between starting at 0.01 is not really much more than the difference of starting at 0.001. Like they're an order of magnitude different, but like the actual space between the two is quite small, but the difference in the outputs is quite drastic, particularly when you think of the maximum value for sine being 1 and the minimum value for sine being -1. They're about as far apart as you'd expect. And the reason why is because those tiny, tiny changes in the inputs make it essentially entirely unpredictable with this particular function about where you're going to end up. And so there is no limit because we're just bouncing back and forth more and more and more violently as we get closer and closer and closer to zero. Here is one where neither the left-hand limit nor the right-hand limit exist. Therefore, the limit overall does not exist. And the reason why these limits don't exist is because we have this kind of like oscillating behavior where we're just bouncing randomly, chaotically back and forth between 1 and -1, and there's no good way to predict where you're going to end up. There's not a value that we. All right, questions with limits? Again? Yeah. Yes.
Like watch. See the flash?
Yeah, sure. You're gonna do like a dollar. Get it back into it. All right, we've got about, I don't know, 7 minutes left. There is a classwork on Pearson. That is a lot of, particularly for today, I think it's like the first 5 for things that you can do. The first 3 are just look at the graph and figure out the limit. The next 2 are like, look at the function and just make a table like what we've been doing in your calculator, plugging values a little bit to the left, a little bit to the right, and see what's going on. And we'll do some algebraic limits starting on Monday. Test. So I'm gonna do just like 1 lesson a day. It's 5